question? No? If not, we can thanks Francesca again. Now we're going to move to Mike Bird, who's going to talk to us about the Doppler wind experiments.
Okay, thanks. So I'm going to talk about the Huygens Doppler wind experiment, which we performed 20 years ago, January. And I'll just run through these slides one after the other. Introducing, first of all, the team. We had people from Germany and also from the United States, 5 in Germany and 6 in the USA. These are mostly people that I had worked with in the past and were well accustomed to working in radio science experiments. So the concept was fairly simple and focused. We wanted to make an in situ determination of the Titan zonal wind along the descent path of the probe. And the idea was to record the Doppler shift of the probe's radio signal both on the Cassini orbiter and also on Earth. So we had a backup on Earth as well as our primary data set, which was coming from the probe support equipment on Cassini. Knowing the radial velocity, and we know this from the altimeter and from other sources, then we can derive the horizontal motion on Titan. And if we assume that the zonal winds are dominant, which they are, in fact, we found out later, then we can determine the zonal wind motion, assuming that the probe is running under parachute with the wind. For this, we need a very stable frequency source, both on the Huygens probe, the so-called TUZO, which was the first element, and then we also needed one on the probe support equipment on the Cassini orbiter. Nothing more than a black box, which produces a very, very stable frequency source, which is then uplinked to the S-band downlink signal. And so we had these observations from Earth planned from the beginning, and it was possible because the Huygens antenna beam was so wide that the Earth was only about 30 degrees from the bore site, and as a result had still plenty of power directed toward Earth. And furthermore, the projection onto the horizontal from the probe Earth vector was very close to that of the probe orbiter direction, but in the opposite direction. And so we're measuring essentially the same thing, but in reverse. And they are tilted enough to each other that we would be able to separate them and maybe tease out the radial wind as well as the zonal wind. So this turned out to be not possible because we lost, unfortunately, the link to Cassini. Oh, let's get a little closer to the mouth. Okay, thanks. Yeah, so we had 2 ground stations on Earth. One of them located at in West Virginia, the NRAO Green Bank Telescope, and the other in Parkes in Australia, close to Canberra. Unfortunately, we didn't have anything in between because there was no big dish between NRAO and Parkes, which had the correct equipment for the particular frequency that we were sending. So the signal paths, as has been mentioned before, we had 2 of them. There was a channel B, which brought us down all of the data, in fact, from the Huygens in situ data. And we had a channel A, which was our experiment, the DWE. It was managed by the TUZO-RUZO combination. At least that's the way it was supposed to be. And then we also had an eavesdropping signal we called a channel C that went to Earth and was received then at Green Bank and at Parkes. Unfortunately, somebody forgot to turn on the RUZO, And I'm not going to go into the reasons why this happened. It's very, very complicated. We had a number of descent sequence software command sequences and a special one for the flight experiment. And somehow the Russo on command was not inserted correctly into the flight sequence, and it was never discovered until it was too late. But we were able to get the channel C data, and as a result, the DWE Earth-based network saves the day. So it's not true. This is a misconception that VLBI saved DWE. It's not right. The VLBI data was actually not a Doppler measurement, but rather a Doppler difference between different stations on Earth, a VLBI measurement. And so the data that was first transmitted back to ESOC on that day was actually DWE data. And in fact, I can show some of it right here. 1 second, we were seeing nothing but noise. And this is the bandpass, which is centered on the predicted Huygens sky frequency. And then just a few seconds later, well, there it is. That's Huygens popping up out of the noise at an unbelievably low power level, but still about 5 dm above the noise. And so we were able to make this measurement. And unfortunately, we had the additional detriment that we had to pause about every 100 seconds while the telescopes moved over to a calibration source for the VLBI measurement. And so you can't hardly see it in this graph, but at every 100 seconds or so, there's a gap of about 80 seconds where we're unable to get any data. We have also a 26-minute gap between the time when the Titan set at Green Bank and when it finally got above the horizon at Parks. And the Cassini loss of link was quite a bit later. The actual impact point, which was just a few minutes after we started the track at Parks, was not observed in our data because, the telescope was not pointed at Titan, but rather at that calibration source. So we don't know if it was bouncing or wobbling around like you were able to detect on the DISR. Here is the height profile that we derived from these data. The Green Bank data are in green, and showing the zonal wind speed as a function of pressure and or altitude. And the Parks data, which is just a little scribble down in the lower left in blue. And the profile with height was approximately what we were thinking it was going to be. It was close to the Blazer model, which is this dashed line and its envelopes. But there was one significant difference, and that was the very, very low speeds at about 20 millibars, about 80 kilometers altitude. So let's just run through this real quickly. Up in the start of the descent, we had a strong prograde super rotation. It was 110 meters per second at 120 kilometers, indicating cyclostrophic balance. Then we had this unexpected wind shear layer between 60 and 80 kilometers. That's 20 millibars, which is still not completely explained, but I have some more on this in a few minutes with update number 2. And down on the surface, the winds were very weak, of the order of 1 meter per second, where we expect to have a boundary layer. But there is also a little update here on the meridional winds, which I'll show just in a few seconds. So the main results. The zonal winds on Titan in the upper atmosphere are prograde. This was the first in situ confirmation of Titan's super rotation. And as a surprise, in fact, we could hardly believe it when we saw it, the zonal wind collapse at 20 millibars at about 80 kilometers. So let me just say a few things about the meridional winds as well. This is an article taken from Icarus. Eric Koshka wrote this, and it shows the trajectory as seen from the east. So you're looking just at the north-south motion of the probe in the bottom 20 kilometers of the descent. And you can see there's some sizable motion. It's not more than a kilometer in any direction. In fact, it's only of the order of a few hundred meters, but it's there. And I think that we would have been able to detect this if we had had the regular DW data. Another thing that has happened since the mission is that there have been a lot of ideas about what this wind collapse is in the 20 millibar level. And in particular, Mike Flaser has been busy with this. He gave a presentation at the EPSC in 2013 and another one at the AGU, Fall AGU meeting in San Francisco in 2020, in which it was rather clear that this minimum is global. It's not just at the Huygens latitude, and it's persistent. So it was there during the entire mission, Cassini mission. These are some slides that Mike showed at that meeting in London. It's just showing where all of the radio occultations have taken place as a function of latitude. On the left, all of the data in altitude, and then a blow up on the right-hand side showing the lower 50 kilometers. But at any rate, they also made a comparison exactly with the DWE at 10 degrees south with what they would have expected from their data. And you can see there's general agreement here. And Mike, in fact, made the statement at one time, I think the minimum in zonal winds near 20 millibars is a real phenomenon. I kind of was hoping that Mike would be here to verify that, or maybe make an additional comment. But I guess he hasn't showed up yet anyway. But okay, so let me continue with just a few more slides showing pictures, which are much easier to digest in this science. These photographs were provided to me by Dennis Matson a number of years ago, and they were all taken at the only science working team meeting in Bonn in April of 2003. Here are four well-known persons in the project standing in front of the place where we're meeting, which happened to be the German Space Agency in Bonn. After we got done with the business, we took a tour of the Effelsberg radio telescope, which is managed by the Max Planck Institute in Bonn. And here's Dennis standing in front of it. And I think most of these pictures are from him, with the exception of this one right here. The next one here shows another member of the team. And in fact, it's the next speaker with his hard hat. And we had to wear these hats because there's always a chance something might fall from about 50 meters under your head. And then we have another couple of famous members of the team here, horsing around at a height of 50 meters about. And so we had this, and then afterwards we adjourned to dinner at a restaurant in the R River Valley. And after that, we tested some wine in their wine cellar. And here is a picture of that event. And in fact, here on the far left is the previous speaker here. So it was a good time, and we enjoyed it thoroughly to be the host of this one meeting. One last slide, and this shows our team on the fateful day in January at ESOC, about an hour before the start of the mission. And so all of these people were there in the team. Yvonne, going from left to right. Yvonne was my student at Bonn, and after she graduated there, she went to Kiel, where she got her PhD. And after that, she studied biophysics in the Saarland. She went to medical school, and right now, she's a radiologist at a clinic in Rostock on the Baltic Sea. Dave Atkinson left Idaho, went to JPL for a number of years, and is now retired and living nicely there in Southern California. Robin Duderoy stayed on for a few years and did some more Huygens work. And then after the money ran out, he became a high school physics teacher in the Bonn area. Mike Allison has retired now from Goddard Space Flight Center and is living in upstate New York. Dirk Pledemeyer is now a professor of electrical engineering at the University of Dresden and has participated in many ESA missions. And that's me there with a tie. It's probably the last time I ever wore a tie. And the last man on the right is Len Tyler, who went on after the Huygens mission to lead the radio science experiment on the New Horizons mission to Pluto. And unfortunately, a couple of years ago, he passed away. So we'll have to add his name to the Golden Legion of former colleagues in Huygens. So thank you very much.
Thank you, Mike. The questions in the room?
So a sociological question. How long was it from the time that it was realized that channel A was not coming down to when you realized that you had Doppler wind data from the effective channel C?
It was a couple of minutes. And well, we saw, of course, with everybody else that the signal had been seen at Green Bank. That was a DWE trace from our spatial receiver there. The only reason why maybe it got confused with the VLBI people is because it was given to Jean-Pierre Le Breton by a member of the VLBI team. Exactly how he got a hold of the data, I don't know. But anyway, from that point on, we knew and we were very happy. We were anticipating that everything was running fine. And then Murphy's Law came in. And we really didn't understand that this was going to happen until we actually saw the data coming down and channel A just wasn't locking at all. Well, it's obvious it didn't lock because it did not have a local oscillator for the receiver. So, yeah, it was about an hour or so. Ups and downs in that day.
Any other questions? If not, we can move to the next speaker. Thanks again, Mike. And so our next speaker without the hard hat will be John Darnicky, talking about the surface science package.